All right, let's go ahead and look at this. Here it is. Any questions?
Yeah.
All right. As always, things start off with a fairly simple problem about nomenclature, etc. We're doing acyl compounds, carboxylic acids, whatever. For our first one, we look at it and say, okay, it's a carboxylic acid. We remember our rule. We want the carboxylic acid carbon to be number 1. Once we've decided where carbon number 1 is, we look to see what else is in the molecule. Well, our chain is 1, 2, 3, 4, 5 carbons. So it's a pentanoic acid as a parent. We also have a double bond out here in carbon number 4. So we're going to change our pentanoic acid to pentanoic acid. And put the E in so that we can tell that in position 4 we have a double bond. So the name would look something like this: 4-pentanoic acid. Any questions? Our next guy is an ester, isn't it? We're going to, first of all, note that the ester portion here is an ethyl group. So we're going to name the alcohol first. It's going to be ethyl something or other. Our parent carbon here, this is going to be carbon 1. That's carbon 2. So it is a 2-carbon parent. That's acetic or ethanoic acid. In carbon 2, we have a benzene ring, so we'll call that a phenyl group. Ethanoic acid is the parent, phenyl group in position 2, and it's an ethyl ester. And the name will be ethyl phenylethanoate. You could also call it ethyl phenylacetate. Ethyl phenylacetate is what you would see if you ever really looked up the compound. Our last one here is a very simple acid chloride. We have 1, 2, 3, 4 carbons in our parent. We're going to let the acyl carbon be carbon number 1. Because we have 4 carbons in our longest chain, and it's an acid chloride, we're going to call it a butanoyl chloride. We look and we see out here in position 3, we have a methyl group. So we simply call it a methyl 3-methyl butanoyl chloride. Any questions? On your actual exam number 2, the nomenclature will be entirely equivalent. So about 3 or 4 problems.
I have a question.
Yeah.
For the ethyl thingy.
This guy.
In the nomenclature, do we account for the carbons on the right side?
That's the ethyl group. First thing you do is name the alcohol. Okay, so if we made this by simple esterification, we would start off with the carboxylic acid and an alcohol. So the first thing you do is name the alcohol. It's ethyl alcohol. ethanol. Then you name the rest of this. It's a phenylacetate. Again, 08 is what we put on to indicate that it's an ester.
We don't have to identify where the phenol's going up because it's only got one spot possible.
It's only one plot, only one spot. All right, a very simple spectroscopy problem here. We have a bunch of C13 data, and we need to figure out what's what. The way I tend to do these is I just look and try to identify what we're looking at based on the series of absorbances. We have a quartet at 22, a quartet at 50. Those two are both methyl groups. You know they're methyl groups because they have 3 hydrogens attached. That's why they're quartets. So we're looking for something that has 2 different methyl groups. Everyone happy with that?
Yeah.
Next we go and we look. We have a doublet, a singlet, a doublet, and a singlet. These are all in the aryl region. So we have 2 doublets and 2 singlets. Go back to, maybe we can't go back. This is a 1,4 disubstituted benzene. Wasn't supposed to disappear that fast, sorry. Remember, with 1,4 substitution, disubstitution, we get 2 singlets and 2 doublets because we have symmetry right down. If we had monosubstitution, we would get 1 singlet and 1, 2, 3, well, depending on whether we have symmetry or not, we would have 1, 2, 3 different doublets. All right, the last one we have here is a singlet at 167. Singlet at 167, remember, acyl carbonyls are around 170, ketones are around 200. If we look, go back to our very first thing here, we're looking for something with 2 methyl groups. There are only 2 of these guys that have 2 methyl groups, aren't they? A, we have a methyl on the ring, and we have a methyl ester. C over here, we have a methoxy on the ring, and we have a methyl ketone. The thing that allows you to tell the difference between these two, this would be a ketone carbonyl at 200. This would be an acyl carbonyl at about 170. Because we're at 167, this is the best fit. Any questions? All right, a very simple acyl transfer question. When we do acyl transfer, we form a tetrahedral intermediate. And this tetrahedral intermediate is going to collapse and something's going to leave. We learned a rule that basically said for anionic leaving groups, the thing with the strongest conjugate acid was going to be your best leaving group. So chloride, HCl is a conjugate acid, pKa of -5, that's the leaving group, as opposed to, say, methoxide, where our pKa would be 16 for methanol. So anyway, which of these? The strongest base, most stable anion, highest pKa, methoxy group, the group having the weakest conjugate acid.
Strong base.
Now, right, you were listening to what I just said. The group with the strongest conjugate acid is your best leaving group. So that one's out. The Phenoxy group is silly. Highest pKa. highest pKa, that's the strongest base, isn't it? Remember, the lower the pKa, the stronger the acid. Strongest base is obviously wrong. Most stable anion will be formed from the strongest acid.
What does conjugate mean? The conjugated acid, what does that mean? When you say conjugated?
Conjugated, oh, you mean like this, conjugate acid base?
Yes.
Think back to general chemistry.
Right.
If we're dealing with a leaving group of methoxide, OCH3 minus, that is derived from the acid methanol by loss of a proton. So the acid is methanol, methoxide is the conjugate base. You can also say, when you're speaking of methoxide, the acid corresponding to it, that's the conjugate acid, is methanol. So that's conjugate acid-base pairs. Spectroscopy of acyl compounds. Frequency of the carbonyl generally parallels the reactivity towards nucleophilic addition. Remember, we said that carbonyls from acid chlorides had the highest frequency absorbance in the IR at about 1800. Amides, which are the least reactive, have a carbonyl absorbance of about 1650. So this one is correct. In the mass spectrum, the most common fragmentation is expulsion of carbon monoxide. Now, you know, that sounds like it could be real, but we know that acyl really often shows up in mass spec. And for acyl to show up, you have to have your CO, so probably this one isn't right. In the proton NMR, carboxylic acid is very highly deshielded. The really tough part here is remembering which end of the spectrum is shielded and which is deshielded. Shielding means you're blocking the magnetic field. So that's going to be a really low value. Deshielded means it's sitting out there, but you can see all the magnetic field is way downfield. We remember carboxylic acids come in at about 12 parts per million. Most highly deshielded that you typically see in proton NMR. That means that A and C are correct statements. All right, next we have some very simple reactions. Our first one, we have an amine, arylamine. This is aniline reacting with an acid chloride. We know that the nitrogen nucleophile will attack the carbonyl. Our best leaving group here is going to be the chloride, and we're going to make the amide. This next guy is a rearrangement reaction, isn't it? We learned two rearrangements, the Curtius rearrangement and the Hoffman rearrangement. This is a Hoffman. We have bromine, we have mercury ion, we're in carbon 10 just as a solvent, and we're going to heat it up. With the Hoffman rearrangement, what happens is we're going to lose the carbonyl group, the CO2, and the bromine is going to go in its place. So really all we're going to do is break this bond right here, and we're going to form the mixed dihalide. And our last one on this page, we have a beta keto acid. Remember, we start here, this is the alpha position, this is beta, so it's a beta keto acid. We know that anything where we have an acid group, an insulating carbon, and then a carbonyl is going to be very subject to decarboxylation. When we decarboxylate, we're going to break this, CO2 is going to come off, and we're just basically left with whatever is on the other side. In this case, the other side is simply acetone. Any question on these three? Anytime you have a beta keto acid, beta carbonyl acid, you will get decarboxylation. Split off this as CO2, and whatever's left is the product. All right, our first one here. We are taking an ester, and we are reacting it with 2,4-pentane dione. We're in the presence of base. We know that pentane dione can form an anion at our central carbon, very stable anion, and that this is going to be a nucleophile towards the carbonyl. When we form our tetrahedral intermediate, ethoxide is going to be our best leaving group. The process looks like this. Here's our attack step. In the second step, we're going to expel our leaving group, and we're left with our adduct. Remember, we lost the ethoxide. These two carbons remain, and they're attached here. Simple carbonyl condensation. Now, dialkyl and diaryl copper lithium reagents are actually really rather useful, interesting things. Way back in Organic 1, we used them for stupid reactions. But here, now that we've done acyl chemistry, we remember that these guys have the ability to react with the carbonyl of an acid halide. We're going to, in this case, simply put the phenyl group right here. Chloride is our leaving group. And we wind up with the aldehyde.
How do we know that was good?
Diaryl copper lithium, aryl group goes to the carbonyl, chloride leaves, and we get, in this case, the aldehyde. We can also make ketones the same way. Remember this lovely reaction from chapter 20. We have red phosphorus, we have bromine. Then we're going to work it up with acid. In this case, we're going to form an intermediate acyl bromide. The enolate from that is going to react with bromine. We're going to put a bromine in the alpha carbon. And all we do is simply brominate like this. It's perhaps the easiest and the nicest way to put a bromine alpha to a carboxylic acid. Any questions on this set? All right, here's the other reaction that we know of dialkyl copper lithiums, diaryl in this case. We know that in addition to reacting with acyl halides, that they can also undergo Michael-style addition. Michael addition is a conjugate addition reaction. In this case, we're going to attack here. The phenyl group is going to be our nucleophile. Think of it as a phenyl anion adding to this carbon. And the product is the ketone. When we do this, remember we lose our double bond. It goes up as the enolate, comes back, picks up a proton from solution. And again, the product is this thing. The bond that we just made is this one right here. These are the carbons of our original starting material. This guy, very simple Fischer esterification, isn't it? If we want to make an ester, we take a carboxylic acid and an alcohol. We do this in the presence of acid. We generate water in the course of this reaction. We either remove the water with some sort of a extraction device, or we just put in tons and tons of alcohol to drive the equilibrium. We are going to make an ester, so we lose the OH, we put the isopropyl group in, and it's simply the isopropyl ester.
Dr. Young, that experiment where you have like a tank of alcohol, is it a tank of alcohol, you pour water into it, it doesn't rise? You know what I'm talking about? Or something, or the other, vice versa? If you had a tank of alcohol and you pour water into it, would it rise, liquid?
With something like 2-propanol, no, it's fully miscible. So. All right, here we have a secondary amine, and we're reacting with an ester. Remember, with all amines, just like we saw with the acid chloride, what happens is the nitrogen nucleophile is going to add to our carbonyl carbon. In this case, our leaving group is going to be methoxide. We are going to wind up with a disubstituted amide. The bond that we just made is between the nitrogen and the carbonyl. Methoxide is our leaving group. Any questions? All right, two more. Here we have a methyl ester, and we are reacting this with ethoxide and ethanol. Oh, I forgot to put the ethanol on the slide here, but what happens here is what's known as an exchange reaction. The ethoxide is going to attack our carbonyl, right? Now we have two possible leaving groups. One is methoxide, and the other is ethoxide. If we lose ethoxide, we just go back, don't we? But if we lose methoxide, and we have lots of ethanol in our pot, what's going to happen is we're going to wind up losing all of this, and we will make the ethyl ester. Whenever you do things like Gleason condensations and stuff like that, you always match your base, ethoxide in this case, with the alcohol and the ester. The reason for that is to keep from getting mixed things, you know, some methyl, some ethyl, whatever. Makes it difficult to purify. So always match your alcohols. And finally, we have malononitrile. Now, malononitrile is going to undergo hydrolysis. We know that nitriles and carboxylic acids are basically equivalent to each other. A nitrile will undergo hydrolysis to give a carboxylic acid. If we do this, this is going to be a diacid with our CH2 in the middle. That's malonic acid. Malonic acid, we know, is unstable. In the presence of acid, it decarboxylates. And what we wind up with is acetic acid and CO2. So two things are happening. Step one, we hydrolyze to the dicarboxylic acid. In the presence of acid, that immediately loses CO2. We wind up with 2-carbon carboxylic acid. Any questions? Your exam will have an entirely comparable set of reactions to these. All right, these are sort of synthetic conversions. And what I ask you to do here is to simply put in either the conditions that you need to do it or the intermediates. Right? Everyone see the game here. We are taking diethyl malonate. Now remember, malonic acid, diethyl ester. So this is a malonic ester synthesis. And we are making this non-conjugated carboxylic acid. The thing that you should always remember about a malonic ester synthesis is that we are going to make a substituted acetic acid. Remember in this last reaction we did, we took malonic acid itself, it decomposed and made acetic acid. So if we do a malonic ester synthesis, we're tacking on an alkyl group of some sort, and we're winding up with a substituted acetic acid. All right, so you remember this fact. You can write it on your palm, I don't know. You remember this fact. And then we look at our final material here and say, okay, we made a substituted acetic acid. These 2 carbons represent our acetic acid, and this is the bond that we just made. Now, in a malonic ester synthesis, we're going to take diethyl malonate and react it with an alkyl halide, right? That's where the alkyl group comes from. The alkyl halide had 1, 2, 3 carbons, and your halogen was here. So now you know the structure of this stuff. 3 carbons with a halogen leaving. Once again, what happens? The malonate anion attacks and bromine leaves. All right, everyone get this one. Now you simply have to draw the structure of the intermediate. The intermediate will have everything we started with here and the carbons of this stuff. It's in the bond we just made, right here. So the intermediate is going to look like diethyl malonate with this attached. Finally, in order to get from here to here, what do we have to do? We have to decarboxylate, don't we? Now we know that when we take a malonic ester and we stick it into acid, then we're going to hydrolyze these into malonic acid itself. Malonic acid is a diacid, decarboxylates. We wind up with the alkyl group we started with that we tacked on, and one of these is going to be the carboxylic acid here, and this is lost as CO2. The conditions you need to write here, simply acid, water, and warm it up a touch. Step one, we hydrolyze the ester. Once we have the diacid, decarboxylates, and we get our product. Any questions? Our next one. Well, we start off here with a very simple reaction. We are taking carboxylic acid and thionyl chloride. We know that this is the standard way to make acid chlorides. All we do is to convert carboxylic acid into the acid halide. Now let's think about what we're doing in this next step. These are the carbons of our acid chloride. So this guy right here. And what we've done is attach a 2-carbon chunk to it. Think back to your reaction page. How do you convert an acid halide into a ketone? We did that on our reaction page. We use a dialkyl copper lithium. The alkyl group must be this ethyl that we stuck on, diethyl copper lithium. Any questions? All right, our next one. Oh my goodness, how did this get in here? This is a 4+2 cycloaddition, isn't it? But we remember how to do those. We remember in our 4+2 cycloaddition, we're going to take a diene, and we're going to take a dienophile, and we're simply going to add them. When we look at our product, we can figure out the structure of our diene and our dienophile. We simply look at the bonds that we made in the cycloaddition. In our cycloaddition here, those are the bonds that we made. These 4 carbons and an oxygen in the ring come from here. That's furan is what it's called. All right, that means that our dienophile simply had 2 carbons and a bromine. The dienophile, therefore, looks like that. Simple Diels-Alder reaction. Now we move up to chapter 20. We're going to take this alkyl bromide, dump in magnesium and ether. What are we doing there? Making a Grignard, yeah. So imagine this as an anion now. Then we're going to dump in little bits of CO2. Add little bits of dry ice. The anion is going to attack, work it up with acid, and we make the carboxylic acid. Any questions on it? 4+2 cycloaddition, followed by carboxylation of a Grignard. All right, in our next one, we have an acid chloride, and we're making an aldehyde. Now, that is kind of a difficult reaction. What we're doing is adding H minus to this. If you want to think of it, H minus as a nucleophile, chlorine as a leaving group. Unfortunately, if we use lithium aluminum hydride, we would reduce this twice, all the way to the alcohol. But we know that there's one magic reagent that allows us to do this. And this is, here's our magic question. How do we do that? Our triterbutoxy lithium aluminum hydride. Remember, this stuff has these three huge groups on it. Because of that, it's very, very slowly reactive, very hindered. This will donate only one hydride, and it really only reacts with acid chlorides, maybe anhydrides too, because it has to be very reactive carbonyl. Here's our reagent for our first conversion here. Now what are we doing? We're taking a carbonyl, an aldehyde here, and we're reacting it with this stuff. What is this? It's the W word. This sounds like a V. The Wittig reaction. So we're going to take this phosphonium ylide. In the Wittig reaction, remember, the carbanion simply attacks. We essentially replace the oxygen here with our carbon. We still are left with a double bond. We just simply change our carbonyl into an alkene. Product would look like this. Now, just in case you want to keep score, these top two carbons came from our acetaldehyde. And this bottom half here came from the Wittig reagent. Here's our first carbon, and of course the benzene ring. Any questions? All right, on these, I tell you in little fine print what's going on. This is a Claisen condensation, this is an aldol condensation. In our previous problem, we had a few things that we remembered. We know that a malonate ester synthesis gives a substituted acetic acid. We know that ethyl acetoacetate will give a methyl ketone. Those are the things we look at so far. Claisen condensation, what does that give us? Claisen condensation gives us a symmetrical ketone. So if we made this by a symmetrical or by a Claisen condensation, then what you want to do is simply look at this and say, okay, we made this from 2 moles of an ester. We did a decarboxylation and all that stuff. That's our step here. All we have to do is identify the structure of our ester. The ester is going to be, you can split either side, of course, because it's symmetrical. The ester is going to come from our carbonyl here. Remember, this was an ester carbonyl. And then whatever group we have attached. Same group shows up over here. So to make this molecule by a Claisen condensation, we would simply need this ester, 2 of them. Step 1, alpha carbon of 1 attacks the second. We get our intermediate. When we dump it into acid, we get decarboxylation, and we wind up with a symmetrical ketone. All right, our next guy we made with an aldol. With an aldol condensation, or aldol type, remember we're taking 2 aldehydes or ketones, and we're condensing these. Originally, we form a beta hydroxy ketone, but in our second step, that dehydrates to give our double bond. So what we need to do is decide which carbons came from our parent ketone or aldehyde. Just work backwards from our dehydration product. When we did dehydration, we formed this double bond here. So that means we can look at this and say, this is the bond we made in our aldol. Originally, we had a hydroxyl group with this carbon, so this used to be a carbonyl. This is the bond we made in the aldol. So to figure out the structure of our aldehyde or ketone, we simply look at what's on this side. We have an aldehyde, a CH2, and a CH3. This is simply 2 moles of propanol. Yeah.
If it's not too much trouble, are you able to go back to that little annotation you had?
Go back to
The annotation?
words.
Yeah, sorry.
Aldol gave us a beta hydroxycarbonyl. So before we dehydrated, before the acid step, there was an OH group here. Single bond and an OH. After we dehydrate, that's when we make our double bond. So the bond that we made was between this carbon and this one. That's it right there. Which means that these carbons came from the aldehyde, CH2, CH3, and it's simply 2 moles of propanol. All right, let's do another one. This is ethyl acetoacetate. We are doing the same sort of thing. We're doing a condensation. Then we're dumping in acid, heating it up. So we're going to decarboxylate. Okay? We know that when we do an acetoacetic ester synthesis, we make what? A methyl ketone. Ethyl acetoacetate always gives a methyl ketone. We're talking about these carbons right here and ethyl acetoacetate. All right, so if we know we're looking for a methyl ketone, these are the 2 carbons. Here's our methyl and our carbonyl. Our central carbon, this guy, is this one, isn't it? Which means that the bond we made in the condensation was that one. And these 3 carbons right here came from these carbons in ethyl acetoacetate. So all we have to do here is to figure out the structure of the alkyl halide. The alkyl halide had a benzene ring, a CH2, and a halogen. let's just call it benzyl bromide. Any questions? The anion at this carbon attacks, this is the bond we make, decarboxylate, hydrolyzes to an acid, decarboxylate, and we get our methyl ketone. All right, our next one we made, again from an aldol condensation. We've done this, we know it. We know that this used to be a beta hydroxy ketone, didn't it? So a hydroxy group used to be here. If the hydroxy group was there before we dehydrated, that means that the bond we made in our aldol is right here where the double bond is. So all you have to do is unwind this. This is the alpha carbon that's going to be our nucleophile. This is the carbon that was a carbonyl. This is our electrophile. So you make this guy into a carbonyl. This is now just a simple hydrogen here, and you're talking about this. Now I've arranged it so it's easier to see, I think. Once again, we make our anion here, attack, and then dehydrate. Any questions here? Ethyl acetoacetate, methyl ketone. Aldol condensation, beta hydroxy ketone, dehydrate to a double bond. All right, alkylation of an enamine. An enamine. Remember, that is a nitrogen attached to an sp squared carbon, so attached to a double bond. Enamine, right? Typically, we would do that with a secondary amine of some sort. The thing to remember here, we're going to alkylate it. That's what our alkylating agent is. It's going to be this guy. And then we're going to dump it into acid and water. What happens is we hydrolyze off the nitrogen part. And we convert the nitrogen into a carbonyl. So in the enamine we started with, this was our nitrogen. That's where the nitrogen was. Alkylation step, we simply added this. That's going to be these carbons here. So, what did our enamine look like? It had our six-membered ring, didn't it? This was a nitrogen with a couple things attached. I don't care what. And because it's an enamine, if this is our nitrogen, our double bond must have been here. And that's what we're doing. Remember, electrons move down from the nitrogen. Here's our nucleophile, it attacks, bromine leaves. Then we work up with acid, convert the imine into a ketone. Any questions? All right. here's what's happening. Anion attacks, bromine leaves, hydrolyze off the nitrogen to give the ketone. All right, our last problem here. Compounds A through F. Compound A on treatment with ethoxide and ethanol, followed by reaction with B, gives C. All right, we've done this a lot, haven't we? We're taking something, reacting it with ethoxide and ethanol. We're doing a condensation here, aren't we? This is one of these condensations. Could be a Glycine, could be ethyl acetoacetate, could be diethyl malonate. But we're doing a simple condensation. So B is going to be an alkyl halide of some sort. So just, we make that note to ourselves, we're looking for an alkyl halide in B. Next, treatment of A with aqueous acid generates 2 moles of ethanol, and a compound which breaks down to give 1 mole of acetic acid and 1 mole of CO2. So, A must be a diethyl ester, right? Because we get 2 moles of ethanol. We also get, after decarboxylation, acetic acid. Now I'm just going to guess here, but this sounds a whole lot like diethyl malonate. And we'll return to that. Most likely a diester, 2 moles of ethanol, gives acetic acid and CO2. That sounds like diethyl malonate. So that's our working guess right now. All right, let's go back to C here. Acid hydrolysis of C followed by decarboxylation gives D. So we're hydrolyzing off our esters, and we are making something that can decarboxylate. So we have D as our product. This is going to be an alkylated, probably malonate. If it's a malonic ester synthesis, which is our best guess right now, then D would be a substituted acetic acid. And finally, if we take F, treat it with terbutoxide and terbutanol, do an E2 elimination, we get styrene, 2-ethenylbenzene. Now when you have a roadmap always ends somewhere. This is where it ends up. What you want to do is to take it and work backwards from wherever you have your entry point. So let's start here with our last step. Oh, we left this out. We left this guy out. Treatment of D with bromine carbonate, that's the Hunt-Stecker reaction, is F. So that's going to be an alkyl halide, and here's our elimination. All right, so let's take our last sets of reactions and work backwards. This is the product we made by elimination. Yeah.
I think you meant to say,
Is EF?
yeah, compound E in the treatment with terbutoxide forms this. So this is a. I think you
So
meant to
E.
write compound E.
Oh, yeah?
Yeah.
Okay. Change that to an E. Sorry.
It's no biggie.
All right, so here's E. Now, the last step we did here was an E2 elimination. We made this stuff by a Hunstucker reaction. We know that's going to give us an alkyl bromide, right? If this is the product we get from our elimination, here's the double bond we made, that means we must have had a halogen attached there. So, our alkyl halide, which is E, not F, must simply be this guy. With this in, we had our leaving group, E2 elimination, lose HBr to make styrene. Now let's work backwards through our Hunstucker reaction. We know that that is going to take a carboxylic acid and convert it to an alkyl bromide. So, compound D here then is the thing we did the Hunstucker on, which means this must have been a carboxylic acid. In the Hunstucker, we simply remove the carboxylic acid and stick the bromine on in its place. This is what we're dealing with. All right, now this roadmap actually comes with a little bit of side information, and let's check that now just to make sure that we're on track. Let's look at the IR spectrum we have for this guy. You also have C13 NMR data. Here's our IR spectrum. This is compound G. Now, if we look at this IR, down here in the OH stretch, we see a very characteristic, big, fat, ugly, broad carboxylic acid, OH. We also see a very nice carbonyl. Here we're about 1700. That would be the carboxylic acid, CO stretch. I don't think I put it on the slide, but it's in your problem. If you look at the C13 NMR of compound D, we have two triplets. If this is our structure, we have two different CH2s, so we would have two triplets in the C13. So this tells us that we're on the right track. This, in fact, is consistent with the structure of D. Now, the other spectrum we have is for A, and that's a proton NMR. Proton NMR of A looks like this. We have, obviously, an isolated CH2, and we have quartet and triplet. Now, the quartet and the triplet tell you we're dealing with an ethyl group, right? Our integration is 4 and 6. So this is an isolated CH2, and this is 2 ethyl groups. That's for compound A. Yeah?
We have different numbers.
You just put one ethyl group on the unit.
2 here.
Oh, okay.
We have
Change
7.
those. Those are wrong. All right. This is consistent with diethylmalonate as A. let's go back to our problem, and we'll start with A. We just decided A should be diethylmalonate. Remember, there's one other piece of information. We were told that if we take compound A and hydrolyze it, that we would get 2 moles of ethanol, 1 mole of CO2, and acetic acid. This will hydrolyze to give malonic acid, that decarboxylates to give acetic acid, CO2, and 2 ethanols. So everything works. Now, we are going to make this stuff, right? We're going to make this by a condensation reaction. Remember, we get a substituted acetic acid when we do a malonate ester synthesis. In malonic acid, this is the carbon, our CH2 right here. This is the carbonyl that was one of the ester groups. So, the bond that we made in our condensation is this one right here. Our diethylmalonate adduct, therefore, looks like this. This is diethylmalonate, acid and water heat, hydrolyze this to the acid, decarboxylate, lose one of them, and we get the acid, the substituted acetic acid. And the last thing we have to do, we have to fill in, is B. Now remember, B is the alkyl halide that we added. This is the bond that we made right here. So our alkyl halide had benzene ring, CH2, and a halogen. Once again, let's call it benzyl bromide. Putting these all together then, diethylmalonate with benzyl bromide gives the adduct. We hydrolyze it to give the carboxylic acid, simple substituted acetic acid. We did a Hunstecker, changed this into a bromine, did an elimination to get styrene. Any questions? Now your exam that you will get on Monday online, remember, please remember to do that. Your exam will have a roadmap of comparable complexity. Isn't this something to look forward to?
Yeah,
Okay, I'm excited. All right, that's it.